Alright, so we have open system. So a system that exchanges matter and energy is an open system. Then we have closed system. System that exchanges energy but cannot exchange matter is a closed system. Then we have isolated system. Isolated system. Any system that cannot exchange matter and cannot exchange energy is called an isolated system. Now number 4, we have an adiabatic system. Any system that cannot exchange matter and energy and cannot do work for the surrounding is called an adiabatic system. So next we'll move to what we call thermodynamic function. Thermodynamic function. So I'm trying to show you everything with regards to the notes before we start the calculation. Thermodynamic function. So a function is a thermodynamic function if it is either a state function or a path function. So we have two types of thermodynamic function. We have the state function, and we have the path function. Whenever a system or whenever you see any terminology in thermodynamics having something like this, changing, is a state function, but the ones not having it is a path function. So example, when you have final enthalpy or final entropy or final of anything minus initial, such a function is said to be a state function. But the ones that don't respond to this is a path function. Example of state function is enthalpy. All those terminologies you get from the laws of thermodynamics, like enthalpy, entropy, gives energy, all those are state function. Why? Work, heat. In terms of heat, I mean Q. The heat going in and out, Q. So these two are path functions. So as we progress, we'll see more of it. So then we move to, so we can say in definition we can say state functions are those functions that do not depend on the path of the change of state or path of the reaction. So the properties can be expressed as final minus initial, while path functions are properties that do not depend only on the final and initial states of a system, but on the sequence of intermediate states on the path of the change of state. So if you know this, let's quickly move over to the laws of thermodynamics. The laws of thermodynamics. So laws of thermodynamics. Laws of thermodynamics. Laws of thermodynamics. So for the laws of thermodynamics, we have the first one, A, and it's called the zeroth law. It's called the zeroth law. So what this law is talking about is that The friend of my friend is my friend. What this law is talking about is that if you carry your girlfriend and go to your friend's house, that your girlfriend is now your friend's friend. So tomorrow, if your girlfriend see your friend, even when you are not there, they are friends. So in stating, this law states that if a system A, let's put it this way. Zeroth law of thermodynamics states that a system A is in equilibrium. A system A that is in equilibrium with a system B. A system A that is in equilibrium, that is in thermal equilibrium with a system B. System A that is in thermal equilibrium with system B is also in thermal equilibrium with system C. Provided that B is in equilibrium with C. A system A is in thermal equilibrium with system B, provided that system A that is already in equilibrium with this is also in equilibrium with this, provided that B and C are in equilibrium. So two systems that are in equilibrium will be in equilibrium to another one, provided the other one is in equilibrium with the middle one. So the friend of my friend is my friend. So that's zeroth law of thermodynamics. This law is supposed to be the fourth law. It was discovered last, but when you check it, it's supposed to come before every other law. That's why we now say that it is the zeroth law of thermodynamics. So we'll move to the second. So we'll move to the first law. The first law of thermodynamics. The first law. So the first law of thermodynamics is the same thing with your law of conservation of energy. It says that energy can neither be created nor destroyed, but can be transformed or can be transferred from one form to the other. Energy cannot be created or destroyed, but can be transferred from one form to the other. Now, if a question come and they tell you using equation, define the first law of thermodynamics, is simply Q is equals to delta U plus W. So this is the same thing as Q is equals to U plus W. So if you don't see some textbooks, you see it as delta U. It's talking about the same thing. So Q is equals to U plus W, and U means internal energy, or you call it enthalpy. So this is the same thing as U is equals to minus the coefficient of this from both sides, Q minus W. So these are the two laws of the first equation. So first law. These are the two equations. This equation is the same thing with this, but it's just when you make internal energy subject formula. So this is the equation of the first law of thermodynamics. So where U equals to internal energy, Q equals to heat absorbed slash or heat released from the system. Now you need to know that W is equals to work. So now that you know this, you also need to know that if you're doing chemistry, if it's chemistry you're doing, chemistry talks about matter, looking into matter, while physics talks about matter and the environment, looking at the environment and matter. So in chemistry perspective, whenever work is done on the system, take it that this person now is somebody enjoying himself. When you are helping it, you are doing work on it, the volume, you'll be compressing it. The volume the volume will be negative. It will be compressed. Whenever you are compressing, it's negative. But because you're doing work on it, the work is positive, is gaining. So when you hear a question say energy was absorbed, that means work is positive. Work of the system is positive. So whenever volume is negative, work must be positive. So that means that Q will be equals to U plus W for absorbed. When you hear absorbed, whenever you hear the question say absorbed. But anytime you hear heat was released from a system, once you hear this, it means that the system is doing work. So when work is done on the sentence saying when work is done on the system, this is our value. W is positive. Q is equals to U plus W. But when work is done by the system, it means heat is released or energy is released. So when work is done by the system, it's just like somebody that is pumping weights. You go to gym. As you are pumping weight, your muscle will be increasing, volume will increase. So anytime volume is positive, work is negative. It's doing work, is releasing energy. And as you are releasing energy, we say that anytime energy is released, be it from the system or from the surrounding, we say it's an isothermic reaction. So but anytime energy is absorbed, we say it's an endothermic reaction. So if you know this, let's go back. So when they say energy is released or work is done by the system, when work is done by the system, is losing energy, so work is negative. This is plus V. So the equation of heat released will be Q equals to U now minus that W. You understand it? So this will now be the equation. So when work is done by the system. So this is the viewpoint of the chemist for chemistry. For chemistry, this is the viewpoint of the chemist. But when is physics? Physics judged by how it's affecting environment. Physics like it when it's favoring the environment. So the physicists will judge it by if work is done by the system. As it's releasing energy, it's coming to the surrounding. So the surrounding will gain energy. So when you gain energy, it's plus W. So the physicist in physics, when energy is released by the system, or when heat is released by the system, is good for the surrounding. So the surrounding is gaining, is endothermic. So that means that when work is done on the surrounding, so this means that when work is done on the surrounding, that means that work is done by the system. So if work is done by the system, work is done on the surrounding is still positive. So whenever work is done on a system, is positive. And when work is done on a system, that means work is done by the surrounding. But when work is done on the surrounding, that means work is done by the system. So when it's done on the surrounding, work is positive. Now when it's done by the surrounding, is losing energy, that means when it's done by the surrounding, that means work is done on the system. So system is gaining, system will be positive, but so surrounding will be negative work. So you understand it now. So with regards to heat now, when work is done by the surrounding, that means the equation now will be by the surrounding will now be Q equals to U minus W. So this is for when work is done by the surrounding. Work is done by the surrounding. So whichever way, it's just about viewpoint. So when is the physicist that is viewing it? Is viewing it in the perspective of how it's benefiting the surrounding. So you see that when it's done by the surrounding, it's done on the system. So when system is happy, work is sad. Remember, surrounding is sad. So it's just with normal day life. For every credit alert you get, somebody is depleted, and when you get depleted, somebody is getting credited. That's how life is. So we move to you knowing it now. Now you know the value. A question can come to tell you what is the conversion of W when energy is released by the surrounding and when energy is absorbed by the surrounding or by the system, whichever way you now know it, and you know the first law and the equation. Now we move to exceptions to the first law. So the law is valid. Energy can neither be created nor destroyed, or can be transferred from one form to the other. That law is valid for ordinary chemical reaction, but when it has to do with radioactivity, radiochemistry, nuclear chemistry, and the rest, you know that is not true. It's not going to be valid. So it's not going to be valid. So you need to know that whenever whenever work is done, or should I say whenever heat goes out of a system, Q is negative, which is normal. Whenever work is done by the system, Q is negative. But whenever work enters, whenever heat enters, Q stands for heat going out and coming. So whenever heat goes out, Q is negative. Whenever heat enters into the system, Q is positive. So a question can come, they ask you what are the conventions of work when, so you know that when heat is going out, it means released. Question can come, they ask you what are the conventions of Q and W when heat is absorbed and heat is released. So into means absorbed. So just know it that once you are releasing, once something is leaving you, is always negative. So once it's done by, when it's done by the surrounding, it's negative for the surrounding. When it's done by the system, it's negative for the system. When it's done on the surrounding, it's positive for the surrounding. When it's done on the system, it's positive for the system. So the only thing you need to notice is that when it's being done on the surrounding, that means it's being done by the system. And when it's being done on the system, that means it's being done by the surrounding. Alright, so with that said, let's move to the second one. So the second one is what we call the second law of thermodynamics. Do not worry, my video is shaking. It's shaking, but I just hope you see what I'm writing. I got a stand, a fake one. Someone just duped me so much money for it, and at the end of the day, it's not working well. Maybe it's part of the reason why I'm not so happy this night. All the same, this needs to be done. So you need to know that, you need to understand that the first law, the zeroth law talks about thermal equilibrium. The zeroth law talks about thermal equilibrium. The first law talks about enthalpy. Then the second law, zeroth law, first law. Second one talks about entropy. And the third law talks about zero, the impossibility of having zero entropy. So it talks about zero entropy. So this is a summary of the laws of thermodynamics. So second law now talks about entropy. Now what is entropy before we start the second law? you need to know that the degree of disorderliness